Hello, everybody. Let me first start by your answers to my questions. I'm very disappointed because I got only 10 answers. So despite the fact that I sent you a reminder, I got only 10 answers, and it's really a pity because I think these are interesting questions, and I would like to have your feedback. Anyway, so let us see the answers, which are quite interesting. Okay, so the first question was about semantics is the study of meaning. Does the computer really understand the meaning of words, things, actions, abstract notions, etc.? And I underlined the word understand. And your answers are, I think you all agree on the fact that the computer does not understand. So Diego Andres says that a computer comes close to understanding, and in many cases, algorithms can memorize meaning. Camille says that a computer is not a living being. Christian says a computer imitates understanding. Ming Qiang says a computer cannot really understand the meaning, but without any further explanation. Kasi Islam says a computer can have a coherent meaning. Julien says computer cannot have the same understanding as a native speaker. Joan says a computer understands how to extract or associate patterns. Maher says doesn't really understand, and Vekatesh has even given a funny discussion between an artificial intelligence and a patient. Okay, so I think you all agree that a computer cannot understand. Now, the very interesting parts are Ezekiel says all depends on how we define understanding. If it is just acting or giving a satisfying answer to a request, it should be able to understand. So I think this is a very important thing. So Ezekiel says if it's just acting, but you can't say just acting. Acting is very important. And being able to act is very, very important. It's not a minor issue. And Maher says that computers act in a way similar to the human's methodology of learning. And that's also very important. So in fact, what happens is that we have different perceptions of the definition of the word understanding and the word meaning. So let me show you a web page. So you see on this web page, it's about a guru. And it says deeper meanings. What is a deeper meaning? Now, I'm exaggerating a bit, but it's to show you that many people use the ambiguity around terms like meaning and understanding. And for example, if you take religions or some ideologies, they will build a set of meanings, of predefined ideas and beliefs. And if you manage to follow this set of meanings, to be compatible with it, to get inserted into this predefined vision of the world, then they promise you will have a deeper meaning, a deeper understanding. Okay, now if you really think about it, we are all beings, whether living or not living, whether humans or animals. Our lives are based also on biology. We have mechanisms for interacting with our environment, and so have also animals and machines. So whether you take humans, animals, or machines, all three exist in the real world and interact with the world. Now, understanding is one of the mechanisms that allow us to interact with the surrounding world. And if we take that definition of understanding, then we share it with animals and machines. Sharing it does not mean that we use it in the same way. The difference between, one of the difference between humans and animals is that humans have a symbolic language. So we can use signs with a signified and a signifier to communicate, and animals do not. Animals do not have symbolic language. They can communicate through gestures, through pheromones, through sound, but it's a low-level communication compared to humans, but it's still a communication. So in fact, if we define understanding and meaning in an operational manner, how does it operate, then a machine can do it in some way. And while machine gets more and more powerful, this will get closer to the way humans operate. So machines will act more and more like humans. Now, does this mean that machines will become humans, like in some science fiction novels? Not necessarily. There will be a convergence. There will be humans saying, we always will have something for ourselves that will distinguish us from machines. Okay. Philosophically speaking, there will always be some difference between humans and machines. But on an everyday level, on the operational level, they will get closer and closer. So this question had the intention of making you think of this, and there is a book I advise you to read. It's called L'Homme, l'Animal et la Machine at CNRS Edition. There has never been a digital copy of it, so I couldn't put the book on Moodle. There is a copy of it at the library, but the library is closed. So I really advise you to find it, buy it, or find it some other way and read it. It's a very, very interesting book comparing humans, animals, and machines. And it's quite cheap. Okay, so this was about the first question. which of course is an endless question. The second question was much more practical. If you had unlimited resources, what part of pragmatics would you implement in your chatbot? I got some very, very interesting answers, and I could say that every one of you has given a different answer. This is very gratifying. So Diego Andres focused on interpreting what the user says. And he says, I would use neural networks to extract the context and meaning from the question. Okay, what you are not saying is how you modelize the context. So neural networks arrive after the modeling phase, and the interesting part is how do you model it? Ezekiel says he would like to predict all possible interactions. Camille mentions humor and irony. Humor and irony are very interesting, and because of, or thanks to Camille, I have put on Moodle a book on the natural language processing of irony. So please do not distribute it. I have bought it. It wasn't very expensive. And it's called Détection automatique de l'ironie. So you would see methods used. How can we get from basic natural language processing to processing of irony with all the intermediate steps? It's really very interesting, and it's a book from 2019, so it's very recent. Christian says that he would like to understand the user much better and keep in memory so the information about the user. So Christian would like to build a relationship between user and chatbot. This is also very interesting. And he mentions metaphors and also dreams. And that's also very interesting because it's something artificial intelligence hasn't tackled yet. Ming-Yang mentions speech act theory. So this is also very interesting, finding out the intentions of the user, but in an open way, rather than having a list of intentions as we saw in our first lab. And Kassi Islam also mentions intents. Julien speaks of quality. This is also a very important topic. How can we ensure quality of understanding and of answers? And a very difficult topic. And as a subtopic of this, you have also fake news. How can you avoid giving fake answers? Johan speaks about information search. So this is a bit independent of the chatbot issues. It's the problem of finding information on the web or elsewhere. Maher speaks about implicature being equivalent to expert systems. So, I'm a bit puzzled about that one. Expert systems were software tools existing 30 or 40 years ago, solely based on decision trees. And expert systems indeed did logical inferences, but I don't see the equivalence between implicatures and expert systems. But of course, you can enrich expert systems so that they understand implicativeness. And Venkatesh would focus on cooperative maxims to guide the conversation, the dialogue. So I think your answers are quite complementary, and they show that you have very nice ideas about what could be done. Of course, doing it is a different issue, and this is why I said I emitted the hypothesis that you have unlimited resources. So thank you very much for these answers. Let us move to today's lecture. So today, I will first briefly mention some other kinds of logic, of first order logic, and then we will move to the semantic web, which is a very, very important subject. So whenever we want to extend first order logic, we call this modal logic, because we introduce new operators, new modalities. One extension is called alethic logic. Alethic from the Greek word aletheia, which is the truth. And here we introduce just two operators. So the whole thing is adding two operators. The one is necessity, and the other is possibility. And of course, the negation of necessity is something which is unnecessary, but not unnecessary in the common sense. Usually when we say that something is unnecessary, we mean we have this implication that it shouldn't be done. Here, something that is not necessary is something that can be done or not, that needs to be done or not necessarily. And then possibility and impossibility. You have some very nice axioms, because it's not just providing the operators, you also have to show how they act. And for example, whatever it is necessary is also possible. This is an axiom. So without this, alethic logic doesn't work. Okay, so this is something that is part of our definitions. When something arrives, it means it is possible. Okay, so you see, I don't use a past tense here because this is not temporal logic. It's not about time. When something arrives, then it means that it is possible, not that it was possible. Whatever is necessary is necessarily necessary. So you see, we can put as many necessity operators. When something arrives, it is necessarily possible. So it's not only possible, it's necessarily possible, and so on. When will you need this? Whenever you will be in a system where necessity and possibility are part of your reasoning. Another modal logic is epistemic logic. Epistemic from the Greek word episteme, science or knowledge. So here the operator is knowing that. This operator K with a subscript A means agent A knows that. So for example, if I take a James Bond movie and the sentence James Bond knows that somebody is a spy, this is an ambiguous sentence. There are two possible interpretations. The first one is there exists somebody for which James Bond knows that he is a spy. And second interpretation, James Bond knows that there exists somebody who is a spy. Okay, so you see the difference between the two interpretations is the first interpretation is James Bond knows who is the spy. And the second interpretation is James Bond knows that somebody is a spy, but he doesn't know who is the spy. Okay, so you see how much clearer the meaning of this sentence becomes when modeled in this way. Now, epistemic logic has its own inference rules. It has a modus ponens. If I know that I have P, and if I know that P implies Q, then I know that I have Q. We have a tautology. I know that I have either P or not P, but this statement is not a tautology. This statement says either I know P or I know not P. So this is not a tautology because there is also the possibility that I don't know whether P is true or not. And we usually admit that if I know P, then P is true, which is not necessarily the case. And also, we also admit that when I know P, then I know that I know P. While Socrates was saying, I know one thing, that I don't know anything. Okay, so what is epistemic logic useful for? One domain of application of epistemic logic is cybersecurity. So believe it or not, you may think these are completely distinct domains, but they are not. Because cybersecurity will build safety rules and safety procedures. And these safety rules rely on the fact of who knowing what, because the root of a computer knows things that an arbitrary user doesn't know. He has access to files that are hidden to most users. So the question who knows what is important. And once you know who knows what, you can start reasoning. And you can find failures in a security system. So you see, epistemic logic has been used in cybersecurity. And alethic logic has been used in decision systems for organizing systems, for detecting intrusions, for finding legal issues, detecting legal problems, and so on. Okay, so this was just a parenthesis about extensions of first-order logic. It was a short one. It's just for you to keep in mind that first-order logic is very powerful, but it's not the absolute tool. There are extensions of it for specific domains. And now let us switch to the semantic web. As this is an important subject, I would like you to let me know by chat what is your level of knowledge of the semantic web. So just type a number between 0 and 5. 0 means you have never heard about it. 1 means you have heard about it, but you don't know what it is. 5 means you are an expert in it. So please, all of you, start typing. Okay. Never heard about it. That's interesting. Okay. So you really have never heard about it. Okay, fine. Now let me show you something. This is a mail I got today. It's internship. It arrived at 7:53 today, so it wasn't planned. And you see the subject, approche sémantique pour reconstituer l'évolution de données territoriales historiques. So it's about administrative, legal, fiscal information, historic information that has to be stored. And it's in the semantic web. You see it's in the title, Stage Web Sémantique. And if it's well paid, 600 euros per month. And if you look at this here, very important, poursuite en thèse possible. So the lucky one that will do this internship will be able to continue on a thesis. So this shows that the semantic web is a widespread technology, which is currently quite important and trendy. And there are fundings for projects in this domain. Okay, let us return to the lecture. Now I will start with this diagram. So this guy is not Putin, it's Tim Berners-Lee. It's the inventor of HTML and therefore of the World Wide Web and therefore of the semantic web. So in a talk he gave in 2000, he introduced this diagram showing different technologies. So the bottom are the simplest technologies, and then when we go up, it gets more and more complex. And incidentally, these technologies have been introduced more or less temporarily in this order, going from bottom to top. So before I give you a more detailed description of ontologies, I will give you an overview of the different technologies in this diagram. So all of these technologies are introduced and maintained by the W3C, the World Wide Web Consortium. Before we start, a small word on the closed or open world assumption. When you model the world, you can do it in at least two ways. The first one is to say that the information I have are exactly all information they are. So here's an example. When I say that Bob is the father of Bill and Bob is the father of John, and I give no other information on Bob, then I can presume that Bob has exactly two children because it's a closed world. The world is only the set of facts I have given and nothing more. In an open world assumption, which means that there may be information I don't know about, the only thing I can say is that Bob has at least one child. So I say one because John and Bill can be names given to the same entity in my model. And of course, Bob can have an arbitrary number of children. In natural language, we have seen implicatures that play somehow with this difference between open world and closed world. So if I tell you that this book has 5 chapters, then by implicature, I mean exactly 5. But logically, it could have more than 5 chapters or even less than 5 chapters if some of the ones I mentioned are the same ones. In the semantic web, we use the open world assumption. And here I have put on Moodle a paper you should, if not read, at least browse. Very interesting paper about logic and probability and how artificial intelligence deals with these two tendencies. Now, let us start with the bottom of the semantic cake. It's called a cake because it has many layers. What is missing are the candles on the bottom. So on the bottom, you have Unicode. Unicode we have seen already. You have characters, and these characters have semantics. I put double quotes to semantics. So they have definitions, in fact, and they also have glyphs. But the meaning in double quotes of a character depend on its position in the encoding and on the writing system it belongs to. And this is really an atomic unit. So we are at the lowest possible level of information. This bottom level, just a moment. The bottom level is shared by Unicode and ERI. So ERI are internationalized resource identifiers, and not this young lady called Iri, that is a Japanese singer. What is an ERI? You should keep in mind that these are atomic elements. So just like Unicode characters are atomic entities, indivisible entities, so are ERIs. And ERIs identify resources. So these resources can be somewhere. They can be on your drive, they can be on the web, no matter. And we can consider an ERI as a token, and this token has semantics, again in double quotes, and the semantics of such a token is the resource which is referred to. And what you really should keep in mind is that we have ERIs and Unicode at the same level. In the same way you say this is a character, you can say this is an ERI, even though an ERI uses Unicode characters in its syntax. On the next level, you have XML. XML is a markup language, which means that you take data and you give structure to the data in an explicit way. The explicit way is by adding tags. So in an XML document, you have data, that we call contents, and you have tags, and these tags are either elements or namespaces or attributes or processing instructions. So it's an heterogeneous document, but most important ingredient are elements, because elements give an XML document a tree structure. So the whole document is an element. It contains sub-elements that contain sub-elements and so on. And at the leaves of this tree, you have text. So when I say text, I mean data, unstructured data. And you also have attributes, which are included in elements, and namespaces. So namespaces are tags to which the element names belong. So an element has a name and it has contents. Contents can be a branch of the tree or just text or attributes. Okay, so we will not spend too much time on XML. It's a basic tool, so you should know how to use XML and what the rules are. We have mentioned the compositionality principle. We have shown that compositionality principle can be applied both in syntax of artificial languages and also in natural languages. So to get the meaning of a sentence, we start with the meaning of leaves and we go up and we compose meanings. Well, it works also in XML. So for example, here I have a document where the main element is body. It belongs to the namespace of prefix XHTML. Here is the IRE of this namespace. So this is the what identifies this specific namespace. Here's another namespace. So you see this doesn't necessarily exist as a resource. It's just an identifier, a unique identifier. And here I have an H1 element with textual contents, and here I have an OL element with sub-elements LI. And in these sub-elements, I have elements in my own namespace, me, which I call town, with the attribute, sorry, this ampersand here shouldn't exist, it's an error, ID equals breast, ID equals plusaname. So I start with the attributes included in elements. Here I have textual contents included in elements, and when I go up, I get the semantics, the meaning of the XML document. So in this case, the meaning is just syntax, the way these data become information. How do they become information? By the namespace. The namespace tells me what each element means. So data becomes information, and information is composed so that I get a structured document containing structured information. Okay, so up to now, we have elementary pieces of information and structure. Now, the next level, called RDF, is about meaning. So we start implementing meaning. In RDF, you only have triples. And your triples are of the kind subject, predicate, object, which looks very much like a sentence with a noun, a verb, a noun, with a subject, a verb, and an object. We call the verb predicate. Now, in a triple, you have, by definition, three entities. These entities are ERIs. So things you define in some way, in a namespace and so on. And the only thing you can do is combine them in triples. Here is an example of a small RDF document. I first define prefixes. So this means I define a prefix. This is the name of the prefix, the tag of the prefix, the label of the prefix. And this is the identifier of the namespace. So this should be unique. When it's an hypothetical URL like this, it means that I'm defining it for this document and it's not really official. When it's existing URL, then it means that this is a well-defined namespace where specific elements have specific meanings. Now, there is a trap here. This is indeed a namespace. FORF means friend of a friend. And this is indeed the signature of this namespace. But when you go there, when you click on this, then you won't necessarily find the description there. So this doesn't mean that you have a resource. It's only an identifier. But usually when you go there, you find some information and you may find documentation on this namespace. And here you have triples. Every triple has three elements and it ends with a period. So here I have the triple Gerald loves Alice. And these three entities are in my personal namespace. I could have looked for a namespace on emotions and sentiments and so on, but just for the sake of the example, I use this imaginary hypothetical namespace of mine. But in RDF, I have the possibility of saying that an instance, an entity, belongs to a class. So here, Gerald is of type, and you see here I have the RDF namespace, is of type FOF person. And this namespace defines what a person is. And loves is a property. Now, with RDF, you can structure information. You need adequate namespaces, and you can have big stores of RDF triples. You can have millions, you can have billions of RDF triples. And you have tools for searching, for making inferences, and so on. Now, if we go one level higher, we find RDFS. Now, was it really important to separate RDF from RDFS? I have no idea. I can only say it's for historical reasons. So at that time, it seemed important to distinguish RDF from RDFS. RDFS gives you some more features. So besides of having instances of classes, you can also define subclasses, ranges, and domains of properties. So for example, here, Alice is of type lovely person, okay? A lovely person is of type class, so it's a class, but it's also a subclass of person. And loves has a domain of persons and a range as a property. And I call this range a lovely person. So you see here I have some more features than in RDF for defining my knowledge domain, for modeling my knowledge domain. Now, what happens if you want to go beyond triples? So for example, if I want to say the statement that Gerald loves Alice is a lie. Gerald loving Alice is a lie. So I have both the statement, Gerald loves Alice, and a statement on the statement. In that case, I use what is called reification. Reification from Latin, res is a thing. Reifying means making a thing out of something abstract. And here I'm reifying the statement. So this statement, Gerald loves Alice, becomes an identifier. It acquires an identifier, and I'm saying that the subject of this statement is Gerald, the object is Alice, and the predicate is loves. So now I have a node for the statement. And then I can say that this statement is of type lie. Okay, so you see that we can go beyond first order logic. In first order logic, it would be loves Gerald Alice, but this is a predicate, and the predicate cannot become the argument of another predicate. So here we can say that this predicate is a lie. This statement is a lie. Here I'm giving some recall on first order logic. These are the things we saw in the last lecture. There's nothing new here. Inference both in usual logic and in mathematics. This is also a case of inference. So what is this? This is the proof that when 5x equals to 3, then x is equal to 3/5. How do I prove it? I have a general rule saying that for all non-zero numbers, when x is equal to y, I have a double implication with x divided by a equals to y divided by a. I have a background fact that 5 is different than 0. And when I apply modus ponens to this, I get the specific case that when x is equal to y, then x divided by 5 is also equal to y divided by 5. And when I combine this with that one, then I get, then that means I can divide both sides by 5 and I get this. So how does RDF translate into first order logic? Well, a triple is just a binary predicate. A triple of predicate type, which means that this is an instance of this class, is in fact a unary predicate. And when I'm in RDFS and I'm using the subclass property, then it's like having an implication with an universal quantifier. So for all x, if x is a lovely person, then x is a person. So lovely person is a subclass of person. And there is also a subproperty property. And in that case, same thing, but with binary predicates, which means that parent is a special case of being an ancestor. Now, on the same level than taxonomies, you have Sparkle. Sparkle is an acronym that looks like SQL, but it's for RDF triples. So a triple store is a database with many triples, but in a store, you can also have an inference engine and obtain inferences. This is something we will see in a lab we will do next week. So next week, we will do a lab on ontologies, implementing ontologies in Python, and using Sparkle to query ontologies in Python. How does a query look in Sparkle? First of all, you give your prefixes, like always. So this is establishing our semantics, the semantics of our vocabulary. What are we talking about? Then you have a select, like in SQL, but you give a triple, and in this triple you can have variables. You can have as many as we want. You can have all three being variable if you want. So variable starts with a question mark, and you can give constraints. So here the constraint is that the first variable is of type person and the second variable is of type person. So this is a query. Find me all people loving other people. Persons, find me all persons loving other persons. Okay, so calling the variable person doesn't mean it is a person. These two constraints give me the fact that I will deal only with persons. So if we attach an inference engine to a triple store, then we can find triples that are not included in the store. And this is what makes Sparkle more important, more interesting than SQL. The name of Sparkle is a recursive name. Sparkle means Sparkle Protocol and RDF Query Language, just like GNU, which means GNU is not Unix. On the same level as Sparkle, we find ontologies. So abstractly seen, ontologies are graphs where concepts are nodes and relations between concepts are edges. So this is the very abstract definition of ontologies. In the frame of the semantic web, ontologies are defined in a language called OL, which we will see in detail, and OL uses RDF, RDFS, and so on. So this is the abstract vision. And as you see here, you have a graph with concepts, concept of teacher, of lecture, of course, of student, of university. And you have relations between concepts. And these relations, of course, are not unique. You can have many different relations between concepts. But since we use triples, And here you see a triple. Teacher gives lecture is a triple. Lecture is part of course, another triple, and so on. We are bound to binary relations. Okay, so in an ontology, by definition of this tool, of this ontology, you have only binary relations. So here, binary relations are sufficient. A teacher gives a lecture. There are cases where you would like more information. And this is another technology which we will briefly see today, which is concurrent to ontologies and called conceptual graphs. And conceptual graphs have the possibility of modeling also non-binary relations. So here you see a binary relation, a lecture is part of a course, but here you have a relation that says a teacher gives a lecture to students. As a sentence, you have a subject, a direct object, and an indirect object. So for doing this is very simple with conceptual graphs. It's a bit more complicated with ontologies. In ontologies, either you will have separate triples, a teacher gives a lecture, a teacher addresses students, so you're splitting your ternary relation into two binary ones, which is not really equivalent, it's a loss of information. Or you can use reification. So you say that giving is a concept, and this concept takes a subject, an object, an indirect object. So reifying means gives becomes a node, a concept, and gives will have relations between teacher, lecturer, and student. So you see, everything is possible, but sometimes it's easier to do the same thing in one technology rather than in another one. Now, there is an initiative of building ontologies for different knowledge domains. Big corporations have their own ontologies because we consider that by using semantic web technologies, you can preserve the heritage of a corporation. Heritage of a corporation is the processes used, the clients, the products, whatever is making a corporation, the status, and so on, history. So corporations want to preserve their heritage, and the semantic web is a means of doing so. But there are also open ontologies for public use. And an ontology ideally models a given knowledge domain. Okay, because in a knowledge domain, you have relations between concepts of the domain. And remember the example we have given in the last lecture. If I take a dictionary allows me to define concepts. I have entries in the dictionary, and for each entry, for each word, I have its description. Okay, but in this description, I use other words. For these, I also have entries. When I start with entry A, I use word B. When I go to entry B, I use word C. At some point, my definition will be circular. At some point, I will return to A. And this means that if I can't break this chain of circularity, I'm bound not to define something, because I will have prerequisites which will be circular. When using ontologies, I don't, or conceptual graphs, I don't have this problem, because every concept is defined by its surrounding concepts. So if I want to define what a student is, I can define it by saying a student is an entity that follows a lecture, is registered in a course, and is registered in a university. And of course, there will be other relations. A student is a special case of a human. A student has some prerequisites, must have a baccalaureate, and so on. There may be many relations needed, but I define a concept only by its relations with surrounding concepts, and that's valid for all concepts. So now you see why ontologies are important, because every part of knowledge we have is connected to other parts of knowledge. And we build like this a big puzzle, and we navigate in this puzzle. So it's a very strong hypothesis, but it's the one used in artificial intelligence today. So it's important to have ontologies for different knowledge domains. And here is a picture showing these ontologies of this linked open data cloud, which you can inspect by going to this URL. So you have 1,239 data sets. And why is it called linked? Because whenever you describe a knowledge domain, necessarily you have to link it with other domains. So in fact, you have some ontologies that are very basic, very low level, very philosophical, high level, very high level, very philosophical. These are called formal ontologies. They define concepts like time, space, being, artifact, and so on. And then you have a bit lower ontologies for general domains, and then again more specialized ontologies for specific domains, and then for subdomains, and so on. And all of these communicate. And this is why you have 1,200 sets, 16,000 links between the sets. So you can consider this as a synthesis of human knowledge. So you may say that Wikipedia is also a synthesis of human knowledge, okay? Wikipedia is represented in natural language. And here you have the representation in a formal knowledge representation language, which is the language of ontologies. And there is a formal version of Wikipedia called DBpedia, which is just one of these ontologies. Okay, so imagine what you have here. Now, how do we represent an ontology? The Web Consortium suggests we use OL. OL means Web Ontology Language, and it's an extension of RDFS. And RDFS is an extension of RDF. So in fact, we use triples with some special predicates. Now, for reasons of complexity of tools, you have many flavors of OL. You have simpler and more complex versions of OL, and one of them is based on description logics. Description logic is an alternative to first-order logic, which is less powerful, less expressive, but also less complex. And we will see description logics in detail. And some versions of description logics, because you see there is an S here, this S means that there are many different description logics. They are based on different ingredients we include or not. And some versions of them are decidable. And here I have the definition. Formal language is decidable whenever you have a Turing machine. So a Turing machine is the tool we use to describe arbitrary formal languages. And it's the highest level of description of formal languages. We have seen irregular languages and context-free language and contextual languages. Well, then you have arbitrary languages which are recognized by Turing machines. And our formal language is called decidable if a Turing machine can represent it, can describe it. So if you want an example of an undecidable language, I cannot give you an explicit example, but I can tell you that this is an decidability problem, and it's equivalent to the halting problem. The halting problem is something much closer to you. Is can we have an algorithm saying whether a program will stop when executed? And Turing has shown in 1936 that this is impossible. The only way to know whether a program will stop after a finite amount of time is to run the program and to wait. There is no algorithm that can tell you in advance whether your program will stop or not. So of course, for the vast majority of programs, this is possible, but it has been shown theoretically that this algorithm, there is no general algorithm for all possible programs. Okay, so decidability in this case is a measure of complexity. Description logics are less complex than first order logic. So just before the break, let me finish with the semantic web cake. On the same level as ontologies, we have rules. For rules, you have different norms. Here's just one of them, SWRL. And rules are just expressions where you have an antecedent and a subsequent. Okay, so it's like inference, and it's very close to implications in first order logic. So you have ontologies on the one hand and rules on the other. And you combine these, staying on the same level as Sparkle. And they are built upon RDFS. So now you see the structure of this, of the semantic cake. Now, unfortunately, what goes beyond this level is still not realized. So this is in the future. It's called unifying logic, which is first order logic, proof, and trust. So the idea is that ideally, whatever you put on the web should be written in Unicode with ERIs so that we know what we are talking about, should be structured in XML as a tree, should use triples with namespaces so that for each entity we know what we are talking about and we know how these are related in a sophisticated way by building ontologies and applying rules. So ideally this should happen, the web should be populated using this kind of pages. And then of course, natural language would be just one way of representing this. We would have a solid World Wide Web, and natural language would be one way of representing pages for humans, and machines would have all the rest for doing reasoning. Okay, so this is really an ideal world. We know that 99% of pages on the web are not like that. Most of them are garbage. Most of them are not even valid XML documents. But Tim Berners-Lee hopes that one day the web will be like that. And going beyond this, he would like whatever we say, whatever we write on the web to be provable. So what we request from science ever since Galileo's, Tim Berners-Lee request for the web must be proven. And then you have this vertical level here called cryptography, where all these levels of information should be encrypted to avoid piracy, to avoid corruption of data. And if you do all that and encrypt it, then you can trust your pages. Then you can trust the web. Okay, so you see, we are still a long way to go to get this. Not because of the incapacity of machines, but because of the way humans use the web, and some drastic changes will be needed. And once you got all that, you need a user interface to communicate with humans. So this is a glance at the future. So maybe you will experience this one day or not. Okay, so this was my general overview of the semantic web cake. Now you know what we are talking about. And after the break, we will look at ontologies in detail. We would see a tool for dealing with ontologies called Protégé. which you will eventually also use in the lab next week. And once we're finished with ontologies and description logics, we may, if we have time, also mention conceptual graphs. So conceptual graphs are the concurrent to ontologies. They are a French invention, and they have many nice features that make them better than ontologies, but of course, very few people use them because the industry of computing follows the Web Consortium, and the Web Consortium has defined the semantic web as being based on ontologies. Okay, so let's take a break and start again at, well, at 11. So see you in a moment. Okay, I hope you all got your coffee so that we can continue. Ontologies are important because many of you will use them in your professional life whenever you will have to model some knowledge domain. And the knowledge domain is not necessarily something abstract like a scientific domain. It can be just a corporation, a company that has products, clients, processes, and so on. Or in a chatbot, if you want to do reasoning, if you want to access information and knowledge and make inferences, then ontology are very popular way with many tools, many implementations, and used by industry. So in this lecture, the goal is that you, of course, discover what ontologies are, but also that you know how to use them and how to model a domain using ontologies. Because it's not just the syntax, it's not just the fact that we have concepts and predicates, is also the way of thinking on how to modeling something, and we will give many examples. And there are many books on the topic. So how to use ontologies in a practical everyday problem. So what is an ontology? It's a set of concepts and a set of relations between concepts. So in fact, it's a graph where concepts are nodes and relations are edges. Then you can also have attributes. Attributes are just pieces of information you attach to concepts. They are not fundamentally different than concepts. They are just attached to them for practical reasons. And then among the relations you can have between concepts, you have hierarchical relations. So remember, in WorkNet, you had synsets representing concepts, and you had relations between synsets, but 99% of these relations were hierarchical. So this is a special case of that. This is an hyperonyme, this is an hyponyme. So ontologies usually have hierarchical relations, and when you have hierarchies between concepts, you can use them to build hierarchies between relations. Mathematically speaking, you have a set of concepts, a set of relations. Hierarchy is represented by a partial order. And then you have relations between relations and concepts. So this is a relation is in fact, if it's a binary relation, it's a pair of concepts. If it's ternary relations, you have more than three. All depends on how you define ontologies. So these are ontologies in general, not specifically all ontologies, in which case you have only binary relations. So here you put a 2 and a 1. And you have attributes, signatures of attributes. So attributes are attached to concepts and they have values in some set of values and so on. So mathematically, this is all it is. Concepts, relations, attributes, and values of attributes. And here's an example. If I take the concept river and the concept of town, I can define a relation, crosses, and the signature of this relation will be a set of pairs of elements. And here I have only one, river, town. A river crosses a town. Now, what is missing in this definition of ontology are instances. Instances and names. Okay. First thing missing are names, that is words or terms attached to concepts. Because this here is language independent. If we want to make it language dependent, we need a lexicon for the ontology, and each ingredient, be it concepts, relations of attributes, becomes names, which we call lexical references. So for this concept of car and typewriter font, we have these names, these lexical references. And what we're also missing are instances. Now this author, Simiano, German author, distinguishes ontologies from knowledge bases by saying that a knowledge base is an ontology plus a set of instances. Okay, so you see the difference. In this definition, an ontology is like in first order logic, you have the abstract world of formulas, where you have ingredients and you combine them in some way. And then we mentioned a model and an interpretation of a formula. Interpretation is a domain and so on. Well, here we have a similar idea. You take your ontology, which is an abstract object, and you add instances to the concepts of to your concepts and to your relations and to your attributes. And then you obtain a knowledge base. What's interesting in this reference, the book by Simiano, is how we populate ontologies. So he claims that we can populate an ontology starting with natural language. And he gives steps. We start by finding terms. Remember, terms can be simple or complex. And named entities. Named entities are specific patterns, noun phrases that refer to entities of the real world. Then, once you have your terms, you can find synonyms. by using what we call distributional semantics, looking at the context of these terms. So if you find a term, two terms used always in the same context, then there is a probability that they are synonyms. Once you have synonyms of your terms, you can define concepts. So a concept can be a set of synonyms, like it is done in WhatNet. And in fact, you can define a concept in an intentional or in an extensional way. And here intentionally I did an error. The error is not intentional, it should be an S here, I'm sorry. Okay, and intentional way is by defining the properties of the concept, and the extensional way is by giving all instances. We've seen that last week. Once you have extracted your concepts from your text, you can define hierarchies of concepts. So if you see a term in some sentences and another term in the same sentences, but also in other sentences, then you can infer that the first one is a special case of the second. Then you can move to relations between concepts, which you can extract from your data. And then you can move to hierarchies of relations. So, for example, when I say that something is a capital of a given country, this is a special case, or not a special case, it's hierarchically underneath the fact of being located in. The capital of a country is always in the country. Then some sentences may give you meta information, so what we call schemes. For example, the fact that rivers are always disjoint from towns. A town cannot be a river cannot be a town. This we can also extract from text. When we always find words representing concepts in different contexts, with different verbs, in different triples, then we can emit the hypothesis that they are disjoint. And finally, on the top of this, we can define general logical axioms like the unicity of the capital, uniqueness of the capital, and so on. Now, of course, one doesn't expect an algorithm to do all that automatically. You would need an extremely large amount of data. Usually what happens is we build algorithms that suggest synonyms, concepts, hierarchies, relations, and so on. And then experts will approve or refute suggestions by the machine. So it's a semi-automatical way. But it's still much faster than doing it all manually. And you can also see that the amount of information you need from each layer increases. You need much more information here than there, much more information here than there, and so on. So this is knowledge extraction, and this knowledge becomes more and more powerful and allows more and more inferences. So the more data you use, the more time you need, the better are your nuggets of information that allow you to get more inferences. So let us take a look now at this specific type of logic called description logics. So we want to make compromises because first order logic is much too complex. So we will reduce expressivity, we will reduce the ingredients, but in such a way that we can still describe general knowledge domains. Only we will need more code, more formulas, more expressions to describe the same knowledge domain. As you can see in the paper I put on Moodle on probability and logics, it says on the first page that to describe the rules of chess in first order logic, you need 10 at the power of 0 pages. So on one page, you can describe all the rules of chess in first order logic. In propositional logic, let me see, I don't want to make a mistake. Propositional logic, you need 10 at the power of 5. So you need 100,000 pages. And in finite automata language, you need 10 at the power of 38 pages. So you're still describing the same domain, namely chess, but the amount of code, the amount of formulas you need is significantly different. So this is what we call the expressivity of language, of knowledge representation language. So remember, in first order logic, we had constants, functions, predicates, connectors. Here in description logics, we have individuals, classes, and roles. Classes are also called concepts and roles are also called properties. Now, if you want to compare with first order logic, individuals are like constants, classes are like unary predicates. So in set theory, classes will be potatoes, and roles are like binary predicates. So they are binary relations between individuals. Here is the default window of this software called Protégé, developed by Stanford. So it's a free software programmed in Java, so it's not very quick. And it allows describing, defining, storing ontologies, and also it allows attaching inference engines to do some reasoning. So it's not Protégé per se that does reasoning, but you can attach different reasoners to it and be able to do inferences. And our example will be an ontology called wildlife. Ontologies can be described in RDF, and RDF can be described in different syntaxes. One of them is XML. So it's not the shortest one, but it's quite clear, and you see what is going on. So here is an RDF document containing an ontology. So this ontology is contained in a file called wildlife.ol, and it has a version. So this happens when I instantiate a new ontology in Protégé by giving the name. And here is the path to get to this file. So for the moment, the only thing I have is the version of the ontology. There is no information. In Protégé, you can visualize your ontologies by graphs where boxes are concepts or instances, so individuals, and different kinds of arrows are different kinds of relations. Here is the ontology where I have defined already many things. So this is a picture once I have defined the ontology. You have a global class, which is called thing and belongs to the namespace of all. So this is hard-coded in all ontologies, thing. And subclasses of thing are animal, carnivore, branch, feuille, plant. And then I have defined subclasses of these and individuals, lion, giraffe. So these are still classes. So in this tab, you see only classes. You don't see individuals. As you can see here, you have different tabs, one for individuals, one for visual representation, and one here for classes. So here is the definition of class animal. Here is the place of this class in the hierarchy. So it's directly underneath all thing, and it has subclasses. And here I have an annotation. So annotations are just comments we add. A comment is in a given language, so we can indicate the language, but otherwise it's just text. And here I have information about this class. So you see, I could say that it's equivalent to something, it's a subclass of something, it has some axioms, it has instances, so these are individuals, and so on. And what I gave here as additional information is the fact that an animal is disjoint from a plant. Okay, so I gave this additional piece of information. An entity, an individual, is either an animal or a plant or something else, but it cannot be animal and plant at the same time. And here's how it looks in XML. So this is the element that defines the class animal. And this element has two sub-elements. The first one is the information I gave that this class is disjoint of that other class. And the second sub-element is my comment. The comments are always for humans. Now, very important, here is the IRE of this class. So this is the identifier of my ontology. It could have been an IRI on the web. I could give a complete URL, but here I'm just referring to a file on my disk to keep it simple. And you may have seen in HTML that this is an internal label, what we call a mark. So in an HTML page, you can put marks, they are invisible. And then when your URL is followed by a hash and the name of the mark, then when you request that URL, the navigator will display directly the mark, the part of the page containing this mark. So here, the same hash is used to give a sub-identifier. So this is the identifier of the ontology. And inside this ontology, I have the identifier of the animal class. So this is the real identification of this new class. Remember, this is an IRI. So in the semantic web cake, it's equivalent to a character. It's really an atomic unit. And this is the plant class, and I'm saying that these two are disjoint. Here I have a RDF triple. The triple is animal, disjoint with plant. Okay, so you have to get used to read XML like this. This is the subject, predicate, object. Another triple, subject, predicate, object. Okay. Now, let's take individuals. I have defined Gigi, Giginu, and Leo as individuals in my ontology. And to Gigi, I gave the class giraffe. So Gigi is a giraffe. Giginu is also a giraffe. And here I have no annotation for Gigi. Here I have the description of its type. So that is the class it belongs to. And I have the information that Gigi and Giginu are disjoint individuals. Okay, so now I know that I have two different giraffes in my ontology. And here is how this looks like. This is how I define an individual, named individual. So why named individual? Because some individuals have names and some individuals are defined in an intentional manner, saying that this individual is in the intersection of this class and that class. So you can define it this way without giving it a name. Okay, so these are named individuals. And here's the name, Gigi and Giginu. And the only thing we know about them is that both belong to class giraffe. And then I'm giving this extra information in RDF saying that all distinct members, that these two are distinct. Now, what is this class type collection? This means that inside this element, distinct members, I have an unordered list of sub-elements. So a collection is a list without an order. I don't need an order to say that two things are distinct. It's commutative. So this collection of individuals, they are all distinct. I could have defined others by placing them here. I introduce the fact that they have to be disjoint. So here is the same thing in formal syntax. Gigi is a giraffe, Gigino is a giraffe, and Gigi is different than Gigino. As is syntax we will see in a moment. This is description logic syntax. Okay, now about roles. A role is a binary relation between individuals, not between classes, between individuals. So for example, mange, eats, is a relation between individuals. So an animal can eat a plant can eat an animal, and so on. So it's a role, and I haven't yet defined who eats whom, but I have defined the role eats, and I'm giving the following information. Eats is the inverse of being eaten by, être mangé par, and eats has a domain, which is the domain of animals. So I don't consider carnivorous plants, carnivorous flowers. I only consider animals eating. And I haven't defined the range. I could define the range and so on. So these are pieces of information I could add concerning the role eats, and I can also give the behavior of this role by saying that is functional, transitive, symmetric, and so on. We will see all that in a moment. Here I'm defining the role mange, eats, and I'm giving these two pieces of information, the fact that it's the inverse of being eaten by, and its domain is the class animal. And this is the same thing exactly in description logic syntax, in mathematical syntax. So to eat is equivalent to is eaten by minus. This minus means the inverse. You have a binary relation, so you take the inverse of the binary relation. So if this is binary relation AB, this will be BA. Now, how do my individuals use roles? So I take the individual Leo, and I'm saying Leo is of type lion, so it belongs to the class lion, and Leo eats Gigi. So this is the description of Leo. It's in the class lion, and these are property assertions. So these are binary relations in which Leo participates. So Leo participates in the binary relation Leo Gigi, which is of type mange, eats. So in the graph, you would draw Leo and Gigi as individuals and an edge between Leo and Gigi, and this edge would be labeled eats. And you see already an inference if Leo eats Gigi, and I know that eats is the inverse of being eaten by, then inference says that Gigi is eaten by Leo, the inverse triple. Here we are, and this is the abstract way of writing it. Leo eats Gigi. Okay, now let's concentrate on the formulas. There are three types of formulas. Formulas that assert, and these describe concepts and roles. Formulas, given terminology, these describe relations. And formulas describing hierarchies of relations. Okay? So the first kind of formulas is the one of assertions of concepts and of relations. So this looks very much like first order logic. Here I'm saying that Gigi is a giraffe. Here I'm saying that Leo and Gigi participate to the binary relation eats. So there is a binary relation of type eats between Leo and Gigi. In this order, the order is important. Now, I'm giving you different kinds of syntax at the same time. Please try to see the relation between them. This is XML syntax. This is mathematical syntax. The formula is the same. Only here, it's in XML, and I have IREs for each individual. I have namespaces for each element, for each relation, for each attribute, and so on. So this is very rigorous. It's linked to some namespaces, to some resources. So this lives in a computer, in computer memory on the web, while this is an abstract mathematical formula. So here it's my responsibility to know what Leo is, what Gigi is, what eats is. It's just syntax. Okay. So you may consider that this is something abstract, and here it's the same thing concretized in an ontology where I know my individuals, I know my properties, and so on. So let us concentrate on the mathematical aspect. But we shouldn't forget that everything I will show you has also a syntax in XML, of course, and we can also obtain it in Protégé. So you have Protégé, human user interface, you have XML, and you have the mathematical syntax. These three are equivalent. Now, on the second level, the T-box terminology, we can compare classes. So for example, we have this operator saying that mother is a subclass of parent. This means that every individual belonging to class mother also belongs to class parent. In first order logic, we would write this. And if you have this belongs to subclass operator going in both sides, then you have an equivalence. So an equivalence means that every member of this class is also a member of this class and vice versa. Starting with concept hierarchy, I can obtain role hierarchy. So parent of is a role. It's a binary relation. Ancestor of is a binary relation. And parent of is a subcase of ancestor of. Every parent is an ancestor. Every ancestor is not a parent. We use the same symbol, even though these are roles while these are classes. Roles can be composed exactly like functions in analysis. When I compose brother of with parent of, I get a subclass of uncle of. So this means that I have a first binary relation going from A to brother of A, and then a second one going from B to parent of B. So of course I have to take it the other way around. I start with parent, A, parent of A, and then I take the brother of the parent. So the brother of the parent of somebody is his or her uncle. And we can say that roles are disjoint. What does it mean? You understand what it means for concepts to be disjoint. It means that the intersection is empty. What are disjoint roles? Well, to understand it, you have to look at roles as binary relations. Binary relations are pairs of individuals, ordered pairs of individuals. Roles being disjoint means they don't share any common pairs. So if A is parent of B, this is disjoint of child of. So A cannot be also child of B. Okay, so we have either A is parent of B or A is child of B, but never both at the same time. Except in the science fiction movie Predestination, as I told you already, where you discover at the end of the movie that you have all persons you saw were the same individual, individual that did time travel, sex change, married himself or herself, and had a child who is also himself, and so on. This is a movie, and in all other interpretations, you have these two roles that are disjoint. Now, starting with this no, not yet. Okay, so let's see some other syntax. In set theory, you have intersection. Well, here you can define intersection of classes, also union of classes, and even complementary. Complementary is used, for the complementary we use the negation sign. So this is the intersection of two potatoes in set theory. This is the union of the potatoes, and this is the complementary of the potatoes. So the domain minus the potato. You have the whole domain when you interpret a formula, and the predicate that we can match to the entire domain is a predicate that is always true. Remember, we saw this in first order logic. We said that when you interpret a formula, to every unary predicate, you can match a subset of your domain, the subset of elements for which this predicate is true. And if you want the predicate for which is true for the whole domain, this is a predicate that is always true. So we denote this by the symbol. So this is the whole domain when you interpret, or a concept that englobes all individuals. And the complementary of this is the empty set. When you interpret, is also the symbol for false, and it has no individuals. We use these for expressions like this. Here I'm saying that everybody is either a man or a woman, or both. So in my domain, in the domain that makes this formula true, somebody is either man or woman or both. And here I'm saying that somebody cannot be a man and a woman at the same time. So it's not very politically correct, I know, but it's a simple example. I should use something different. I could take cats and dogs and etc. And this one, we use the symbol for truth. Here it means the complete set. In all, it will be all thing. And this will be all nothing, all nothing. Now, starting with this slide, notation becomes more difficult. So here you need some effort to understand notation. And I'm sorry for that, but I haven't chosen this notation. Others have done it, and I have to explain it to you. We're using the existential operator followed by a role. Okay. And this role is followed by a period and some concept, like here. We call this an existential restriction. Existential because we use the existential quantifier, and restriction because we take elements that participate at the role, so they are left parts of binary relations in this role, restricted so that the right part of the binary relation is in the concept given. So let me explain. Maybe I can write. Okay. So imagine we have an individual A and an individual B, and they belong to the role parent. What is this exists parent dot daughter? This is a concept. It's a set of individuals. Which individuals? It's the set of individuals A that participate as left parts in a relation of the type parent such that B belongs to daughter. Okay. So whenever I have this situation, such an A belongs to this thing, exist parent dot daughter. So this expression is a way of saying I want those individuals that are parents and have at least one daughter. Why at least? Because they can participate to other relations of type parent, and they may have other children that are not daughters. So this means I want all of those who are parents of at least one daughter. When I write this, it means I have no restriction on the concept of the right part of the binary relation. So here I want those who are parents of at least one element that can be arbitrary, since here I have no restriction. We will make some exercises for you to get used to this notation, which is not very easy to grasp. In protégé, as you can see, this is given by expressions like this. I want to express the fact that plantes comestibles sont des plantes qui sont mangées par des herbivores et par des carnivores. Here I have plant comestible, which is a subclass of plant. And I'm saying that plant comestible is a subclass of mangé par some carnivore. So there exists a carnivore such that plant comestible is mangé par. So an eatable plant belongs to the class which is given by there is at least one, by all those who participate to is eaten by with the second element in the class herbivore. So eatable plants are those that are eaten by herbivores. So you have a relation A to B, where the relation is eaten by, and B belongs to herbivore. So all those who are eaten by herbivores are eatable plants. Now, like the existential restriction, we have also the universal restriction. And here we have a trap, because this notation means two different things at the same time. It means in a symmetrical way to existential restriction those that have only daughters. So this means all the A's that participate to a parent binary relation, the target of which are all daughters. But it also means those who are not parents. So I know this is counterintuitive, but in this expression, I have also all those who are not parents at all. Why? I have no idea. It's defined like that for historical reasons. Somebody had this right idea. Probably there is a justification, but it's something you have to learn. It's like that. And it's a trap. So the trap is among those who are parents of only daughters, I have also those who are not parents at all. And if you think about it, can we say that somebody that has no children has only daughters? Yes. I can say that if I have no children at all, I have only daughters. I can also say that I have only boys, sons. Okay. It's a philosophical question, and here this choice has been made. So question, what does this mean? Well, I take both ways of interpreting the formula. The first one is I take those who are parents of any kind, of any type, and those who are not parents at all. So in fact, this is systematically the whole set, the whole domain, because I have those that participate to a parent relation without any restriction on the target of the binary relation, and I have those that do not participate. So I have everybody. Okay. As I said, we can consider all of these expressions from a set theoretic point of view. So we can take interpretations, and interpretation is exactly the same as in first order logic. I need a domain, and I need for each individual in my formula, I need an individual in the domain. And for each class in my formula, I will have a subset of the domain, a potato. And for each role in the formula, I will have a set of pairs of elements of the domain. So what will be the set theoretic interpretation of this? Existence R dot C, it will be the individuals X, such that some successors of this X are in C, Ci, the interpretation of C. And this here will be all the successors of Xi are in C. And when I say that all the successors are in Ci, this is also true when X has no successors at all. And here is the example in the protégé of the universal restriction. Mange only feuilles. So a giraffe is a subset of herbivore intersection with either those who don't eat anything or those who eat only leaves. Okay. So here the idea is to say that a herbivore will eat also other parts of plants, not only leaves, also roots and branches and so on, while a giraffe will eat only leaves. A giraffe will never eat the stem of a tree. It will eat the leaves of the tree. So I'm saying that a giraffe is a herbivore intersection with this class, and this class is the class of those who either don't eat at all, if they exist, and those that eat only leaves, so that participate in eating relations with elements, only elements in the class leave. Okay, now we have some gadgets in the syntax. Besides of the exist symbol, we can use bigger equal than n, smaller equal than n, or just an n. In this case, it's at least n successors. Well, what I call a successor is the right part of the binary relation. So when I say exists R C, it means that I have at least one successor. When I put this, I mean at least n successors, and this at most n successors. Now, be careful, because here we are in abstract theory. So these are individuals. It's like defining constants in first order logic. It's not interpretation. Constants are names. Individuals are names. When I interpret my formula, I may very well send these names, different names, to the same object in my domain. Okay, so don't confuse things. Here, when we say more than n, we mean more than n individuals with different names. But when we interpret this, we have no guarantee that we still have more than n different entities in the domain. Another interesting notation is self. This means that I'm looking for the set of elements for which the role R is reflexive. A binary relation is reflexive when you have A. For example, equality is reflexive because A is equal to A, whatever A may be. So equality is always reflexive. Other relations are reflexive only for some elements. So for example, if I take the binary relation that sends a number to its double, then this one is reflexive only for 0. The double of 0 is 0. Okay, so if R is a role, then this is the set of elements for which the role is reflexive. The set of pairs AA in this binary relation, if they exist. If I take, for example, the relation A smaller than B, strictly smaller, then there is no such number. There is no number which is strictly smaller than itself, at least no finite number. We can define the inverse role. We just invert all pairs. We can define the universal role, where we have all imaginable, possible and imaginable pairs. And we can define the transitive closure. So what is a transitive closure? Transitivity is whenever you have a binary relation AB and a binary relation BC, that you also have AC. Now, if you start with some pairs, then your relation may not be transitive. Some pairs may be missing. If I add all the pairs that make this relation transitive, then I obtain the transitive closure. And a closure is always a minimal set. So it's the smallest set, the smallest role that is transitive and contains R. So I've given you some ingredients, and here's a list of all of these. Here is how I can define a concept, either by giving a list of names or by intersecting under concepts, by taking the union of other concepts, the complementary, by using existential restriction, universal restriction, gadgets, self-reflexivity, and so on. Here is how can I define a role. And here are the different expressions I can write. I can say that these individuals participate to that concept, to that relation. They are equal or disjoint. I can say that this class is a subclass of that class. This role is a subclass of that role. I can compose roles. I can say that they are disjoint. The idea of having more than one description logics is to define these as ingredients we will add or not to the description logic we will use. So as you can see here, these ingredients have labels. So for example, O means I can describe a concept in an extensional way. I have the possibility of giving the list of all individuals in this concept. If I want this feature, then I ask for the ingredient O. I is the possibility of having inverse roles. If I want this ingredient, I ask for the ingredient I, and so on. So you see that each ingredient I add will give me more expressivity. I will write better formulas, more powerful formulas, but it means also more calculations. Because once I have the possibility of adding this minus to define inverse roles, it means that I can put this everywhere and the machine will have to calculate inverse roles of any role I may use, and so on. A common choice of description logic is Sroik with these 5 ingredients, S, R, O, I, Q, and this is what is used in OL version 2. So this is a common set of features, which is nice to know and to be able to use, but one can define others, and one can also use less ingredients in description logic. So let's do an exercise. This is a not very common way of describing an ontology, but it's practical for the exercise. So the idea is that in this graph, inside the circle, I have the name of an individual. So each node of the graph is an individual. Arrows are relations. So R is a role, and DE is participating to this role. G has an S relation with itself. So S is a role, and I have S being a reflexive for G. So GG is a pair belonging to role S, and GD also belongs to S, and EF also belongs to S. And finally, capital letters next to nodes are classes. D belongs to A, E belongs to A, F belongs to A and B, and G doesn't belong to any class. So this is my notation, a notation used only in this particular case for this exercise. And the exercise is find out what these expressions mean. So what will be A union B? So D belongs to A, E belongs to A, F belongs to A and to B. So D, A union B will be D, E, F. What will be this? Exist S dot A. So these are elements that participate to an S relation, the target of which is in A. So is G in this set? Yes, because G participates to S with the target D being in A. So G belongs to this. Let me write. So here I have G. Is D in this set? No, because D is not the origin of any S relation. E is the origin of an S relation, the target of which is F, and F belongs to A. So E also belongs to this set. So here is the answer to this. What will be this expression? Exist S dot complementary of A. Does G belong to this set? Well, G participates to an S relation, the target of which is again G, which is not in A. So G belongs to this one. Does E belong to this one? No, because E participates only to one S relation, and the target of which is in A. So it's not in complementary of A. So this will be only G. What is this for all SA? So we need those that participate. So either, so this is the trap. So either do not participate to any S relation, and this is the case of D. You see D has no outgoing S arrow. It's the case of F. F has no S outgoing arrow. E has an S outgoing arrow. G has an S outgoing arrow, even two. Now, for those who participate to an S relation, we want all the targets to be in A. So G has a target G, and G is not in A. So G is not in this set. E has a target F. It's the only target of E for the S relation, and it belongs to A. So E is part of this. So let's do this one, and then we move to the next slide because we don't have much time. I know that this here is GE. And now I want all elements that participate to an S relation, the target of which is GE. So G participates to an S relation, the target of which is G. So G belongs to this one. Sorry, to this one. Does E belong to this one? Well, E belongs, participates to an S relation, but the target is not in GE. So this here is only G. And if I continue again, I will find G and again G and again G. And so I could add as many, there exists S dot, as many as I want. I will always get simply G. Okay, so I hope this has given you a better feeling about these notations. Another exercise, all trucks with trailers have exactly 18 wheels. If I write, so this is the class of trucks. And among trucks, I want those with trailers. So I can say, I take trucks that have a trailer. So these are all objects in the world that have trailers, and these are trucks. So in the intersection of the two is the class of trucks with trailers, which have exactly one trailer. And I want to say that all of these have exactly 18 wheels. So this class, the intersection I just defined, is a subclass of those objects in the world that have exactly 18 wheels. Now, is this true? Well, as I said, this means that we have 18 individuals of class wheel. But when we interpret this formula, do these 18 individuals get mapped to 18 different objects in my domain? There is no guarantee for that. So if I want to be sure that I have exactly 18 different wheels in any interpretation, I have to write pairwise inequalities. So I have to name these wheels, wheel number 1, wheel number 2, wheel number 3, and write all the pairwise inequalities. And there are many of them. There are 18 factorial different pairwise inequalities. Okay, so now normally we should stop, but I will take a few more minutes of your time just to give you an alternative to ontologies. So I will not enter the details because it needs more than 2 minutes to really understand the differences. But what you should keep in mind is that conceptual graphs are bipartite graphs where you have nodes for concepts, which are drawn by squares, and nodes for relations that are drawn by ellipses. And arrows go always from relations to objects. Objects can be concepts or individuals. And these arrows are numbered. It's because you know that when you give a predicate and the arguments of the predicate, the order of arguments is important. So this is the order of arguments. So has a pet, has a subject, and an object. 1 is the first argument, 2 is the second argument, and so on. And here I'm describing this picture. So I have a monkey called Cheetah that plays with a car. I have a boy called Fox that plays with the same car, and the boy also drives the car. And this pet this pet belongs to the boy. So this graph gives me an interpretation of this image. Now, the interesting thing is that when using conceptual graphs, queries become graph homomorphisms. So what is a homomorphism? It's a mapping between two structures that respects internal operations. In our case, whenever I have an edge between two nodes, I map the nodes, then I also have to have the edge. So this is a graph homomorphism. And in our case, it sends nodes to nodes, edges to edges, and also it respects edge numbers. So when I have the order of my arguments and I send them to the other graph, then I must keep the same order. Now, this homomorphism must be a hyperonyme relation. Why do I need a query? I have here a very practical application. Imagine you have a website with millions of pictures, or photographs, and you would like to search this database of images. One way to search is by giving keywords. But keywords are like bags of words. You have no relation between them. If you describe your images using this kind of graphs, then you can search with more sophisticated queries. So, for example, the query, I'm looking for a child that has a pet, and together they use a toy. This is quite a sophisticated query, but if my database has millions of images, then chances are that there are some images like this. So I'm not saying what kind of animal, I'm not saying what kind of child, and I'm not saying what kind of toy. Having a pet is a special case of having. A monkey is a special case of animal. A boy is a special case of child. Playing is a special case of using, and a car, a toy car, is a special case of toy. So here I have mappings which are all hyponyms. Has a pet is a hyponym of has. This map, phi, is a graph homomorphism. You can verify that it respects all relations and it respects ordering of arguments. So this map exists and is a graph homomorphism. This means that this here is a result of this query sent to the database of images. If I'm asking for child drives car, again, I get this. So this image is a result. So not only I have the result, but I also have the information. What is the boy here? And what is the car? But if I ask for a monkey drives a car, then even though I have here an homomorphism, no, a mapping, here a mapping. Oops, sorry, no, that one is not correct. Drives plays with is not a special kind of drives. So I have mappings here, but I don't have a mapping there. So this is not a result to this query. And a car drives a child. I have boy drives and car, but here the order is not the same as there. So again, this is not an homomorphism. So I will not get that result. So this was just a very quick way of showing you the elegant way in which conceptual graphs allow querying, intelligent querying of knowledge bases. Now it's time to take a break. This afternoon, we will do a lab on frequentist methods with a corpus. So I wish you all bon appetit and see you at 1:30 for our lab.